Welcome to the series of e-learning modules on assignment problem and Hungarian problem without proof. By the end of this session, you will be able to explain mathematical model of assignment problem, explain solution methods of assignment problems, explain variations of assignment problem, explain traveling salesman problem, explain how to solve a typical assignment problem. Let us start with an introduction. An assignment problem is a particular case of a transportation problem where the sources are assigned and the destinations are tasks. Furthermore, every source has a supply of 1 since each assignee is to be assigned to exactly one task, and every destination has a demand of 1 since each task is to be performed by exactly one assignee. Also, the objective is to minimize the total cost or maximize the total profit of allocation. The problem of assignment arises because the resources that is available, such as men, machine, etc., has varying degree of efficiency for performing different activities. Therefore, the cost, profit, or time of performing different activities is also different. Thus, the problem is how the assignments should be made so as to optimize the given objective. Some of the problems where the assignment technique may be useful are assignment of workers to machines, salesmen to different sales areas, clerks to various check counters, teacher to classroom, vehicle to routes, contracts to bidders, etc. Mathematical model of assignment problem. Given n resources or facilities, n activities or jobs, and effectiveness in terms of cost, profit, time, etc. of each resource for each activity, the problem lies in assigning each resource to one and only one activity so that the given measures of effectiveness is optimized. The data matrix for this problem is shown in the table. It may be noted that this data matrix is the same as the transportation cost matrix, except that supply or availability of each of the resources and the demand at each of the destination is to be taken to be 1. It is due to this fact that the assignments are made on one-to-one basis. Let Xij denote the assignment facility I to job j such that Xij is equal to 1 if facility I is assigned to the job j, otherwise 0. Then, the mathematical model of the assignment problem can be stated as minimize z is equal to summation I is equal to 1 and summation j is equal to 1 Cij into Xij. Subject to the constraint summation Xij is equal to 1 for all I, summation Xij is equal to 1 for all j, and Xij is equal to 0 or 1 for all I and j, where Cij represents the cost of assignment of resource I to activity j. From the above discussion, it is clear that the assignment problem is nothing but a variation of the transportation problem with two characteristics. The cost matrix is square matrix, and the optimal solution for the problem would always be such that there would be only one assignment in a given row or column matrix. Remark: in an assignment problem, if a constant is added to or subtracted from every element of any row or column of the given cost matrix, then an assignment that minimizes the total cost in one matrix also minimizes the total cost in the other matrix. Solution methods of assignment problem. An assignment problem can be solved by the following 4 methods: enumeration method, transportation method, simplex method, and Hungarian method. Enumeration method. In this method, a list of all possible assignments among the given resources, that is men, machines, etc., and activities, that is jobs, sales areas, etc., is prepared. Then, an assignment that involves the minimum cost or maximum profit, time or distance is selected. If two or more assignments have the same minimum cost or maximum profit, time or distance, the problem has multiple optimal solutions. In general, if an assignment problem involves n workers by jobs, then in total there are n factorial possible assignments. For example, for n is equal to 5 workers by job problem, we have to evaluate a total of 5 factorial or 120 assignments. However, when n is large, the method is unsuitable for manual calculations. Hence, this method is suitable only when the value of n is small. Transportation method. Since an assignment problem is a special case of the transportation problem, it can be solved by transportation methods as already discussed. However, every basic feasible solution of a general assignment problem that has a square payoff matrix of order n should have m plus n minus 1 is equal to n plus n minus 1 is equal to 2n minus 1 assignments. But due to the special structure of the problem, none of these solutions can have more than n assignments. Thus, the assignment problem is inherently degenerate. In order to remove degeneracy, n minus 1 number of dummy allocations, deltas or epsilons will be required in order to proceed with the algorithm for solving a transportation problem. Thus, the problem of degeneracy at each solution makes the transportation method computationally inefficient for solving an assignment problem. Simplex method. Since each assignment problem can be formulated as a 0 or 1 integer linear programming problem, such a problem can also be solved by the simplex method. As can be seen in the general mathematical formulation of the assignment problem, there are n into n decision variables and n plus n or 2n equalities. In particular, for a problem that involves 5 workers or jobs, there will be 25 decision variables and 10 equalities. This again is difficult to solve manually. Hungarian method. The Hungarian method of assignment, developed by Hungarian mathematician Dr. Koenig, provides us with an efficient method of finding the optimal solution without having to make a direct comparison of every solution. It works on the principle of reducing the given cost matrix to a matrix of opportunity cost. Opportunity costs show the relative penalties associated with assigning a resource to an activity as opposed to making the best or least cost assignment. If we can reduce the cost matrix to the extent of having at least one zero in each row and column, it will be possible to make optimal assignments when the opportunity costs are all zero. Let us now discuss about some of the variations of the assignment problem. Multiple optimal solutions. While making an assignment in the reduced assignment matrix, it is possible to have 2 or more ways to strike off a certain number of zeros. Such a situation indicates that these are multiple optimal solutions with the same optimal value of objective function. In such cases, the most suitable solution may be considered by the decision maker. Maximization case in assignment problem. There may arise situation when the assignment problem calls for maximization of profit, revenue, etc. as the objective function. Such problems may be solved by converting the given maximization problem into a minimization problem in either of the following 2 ways. Put a negative sign before each of the payoff element in the assignment table so as to convert the profit values into cost values. Locate the largest payoff element in the assignment table and then subtract all the elements of the table from the largest element. The transformed assignment problem so obtained can be solved by using the Hungarian method. Unbalanced assignment problem. Unbalanced assignment problem. The Hungarian method of assignment discussed above requires that the number of columns and rows in the assignment matrix be equal. However, when the given cost matrix is not a square matrix, the assignment problem is called an unbalanced problem. In such cases, dummy row or column are added in the matrix with zeros as the cost element in order to make it a square matrix. For example, when the given cost matrix is in the order 4 by 3, a dummy column would be added with zero cost element in that column. After making the given cost matrix a square matrix, the Hungarian method can be used to solve the problem. Restrictions on assignments. Sometimes it may so happen that a particular case, say a man or machine, cannot be assigned a particular activity, say territory or job. In such cases, the cost of performing that particular activity by a particular resource is considered to be a very large, written as M or infinity, so as to prohibit the entry of this pair of resource activity into the final solution. Traveling salesman problem. The traveling salesman problem may be solved as an assignment problem with two additional conditions on choice of the assignment. That is, how should a traveling salesman travel starting from his home city, the city from where he started, visiting each city only once and returning to the home city so that the total distance, cost or time covered is minimum. For example, given n cities and distances dij, cost cij or time tij from city I to city j, the salesman starts from city 1, then any permutation of 2, 3 up to n represents is equal to an optimal route that is able to achieve the objective of the salesman. To formulate and solve this problem, let us define xij is equal to 1 if salesman travels from city I to j or 0 otherwise. Since each city can be visited only once, we have summation xij is equal to 1, where j is equal to 1, 2 up to n, and I is not equal to j. Again, since the salesman has to leave the city each except city n, we have summation xij is equal to 1, I is equal to 1, 2 up to n minus 1, I not equal to j. The objective function is then minimize z is equal to summation I equal to I, summation j equal to 1. Here we do not require dij equal to dji, therefore dij is equal to infinite for I equal to j. However, all dij's must be non-negative, that is dij is greater than equal to 0 and dij plus djk is greater than equal to djk for all I, j, k. The Hungarian method minimization case can be summarized in the following steps. Step 1. Develop the cost table from the given problem. If the number of rows are not equal to the number of columns, then as required a dummy row or dummy column must be added. The cost element in the dummy cells are always 0. Step 2. Find the opportunity cost table. Identify the smallest element in each row of the given cost table and then subtract it from each element of that row, and in the reduced matrix obtained from step 2a, identify the smallest element in each column and then subtract it from each element of that column. Each row and column now have at least one 0 element. Step 3. Make assignments in opportunity cost matrix. The procedure of making assignments is as follows. First round for making assignments. Identify rows successively from top to bottom until a row with exactly one 0 element is found. Make an assignment to this single 0 by making a square around it. Then cross off all other zeros in the corresponding column. Identify columns successively from left to right hand with exactly one 0 element that has not been assigned. Make assignments to this single 0 by making a square around it and then and then cross off all other 0 elements in the corresponding row. Second round for making assignments. If a row or column has 2 or more unmarked zeros and one cannot be chosen by inspection, then choose the 0 cell arbitrarily for assignment. Repeat steps A and B successively until one of the following situations arise. Step 4. Optimality criteria. If all 0 elements in the matrix are either marked with square or crossed, and if there are exactly one assignment in each row and column, then it is an optimal solution. The total cost associated with this solution is obtained by adding the original cost figures in the occupied cells. If a 0 element in a row or column was chosen arbitrarily for assignment in step 4a, there exists an alternative optimal solution. If there is no assignment in a row or column, then this implies that the total number of assignments are less than the number of row or column in the square matrix. In such a situation, proceed to step 5. Step 5. Revise the opportunity cost matrix. Draw a set of horizontal and vertical lines to cover all the zeros in the revised cost matrix obtained from step 3 by using the following procedure. For each row in which no assignment was made, mark a tick. Examine the marked rows. If any 0 element occurs in these rows, mark a tick, and in the respective columns containing those zeros, examine marked columns. If any assigned 0 element occurs in those columns, mark a tick to the respective rows containing those assigned zeros. Repeat those processes until no row or column can be marked. Draw a straight line through each marked column and each unmarked row. If the number of lines drawn or total assignments is equal to the number of rows or columns, the current solution is the optimal solution. Otherwise, go to step 6. Step 6. Develop the new revised opportunity cost matrix. From among the cells not covered by any line, choose the smallest element. Call this value K. Subtract K from every element in the cell that is not covered by a line. Add K to every element in the cell covered by the 2 lines, which is intersection of 2 lines. Elements in the cell covered by 1 line remain unchanged. Step 7. Repeat steps. Repeat steps 3 to 6 until an optimal solution is obtained. Let us take an example to understand the assignment problem using the Hungarian method. Example 1. A department of a company has 5 employees with 5 jobs to be performed. The time in hours that each man takes to perform each job is given in the effectiveness matrix below. How should the jobs be allocated, 1 per employee, so as to minimize the total man hours? Column represents the employee A, B, C, D and E, and row represents the jobs 1, 2, 3, 4 and 5 respectively. The values in each box represents the time that each man takes to perform the job in hours. Solution. By applying step 2 of the algorithm, let us get the reduced opportunity time matrix by taking the minimum element in the rows and subtracting this element from all elements in their respective row. The reduced matrix is shown in the table. Step 3 and 4. We examine all the rows starting from A, one by one, until a row containing only single 0 element is located. Here rows A, B and E have only one 0 element in the cells A2, B1 and E4. Assignment is made in these cells. All zeros in the assigned columns are now crossed off as shown in the table. We now examine each column starting from column 1. There is 1 0 in column 3, cell C3. Assignment is made in this cell. the cell C5 is crossed off. All zeros in the table are now either assigned or crossed off as shown in the table. The solution is not optimal because only 4 assignments are made. Step 5. Cover the zeros with minimum number of lines which is equal to 4 as explained below. Mark or tick row D since it has no assignment. Tick columns 1 and 4 since row D has 0 element in these columns. Tick rows B and E since columns 1 and 4 have an assignment in rows B and E respectively. Since no other rows or columns can be marked, draw straight lines through an unmarked rows A and C and the marked column 1 and 4 as shown in the table. Step 6. Develop the new revised table by selecting the smallest element among all uncovered elements by the lines in table, that is 2. Subtract k equal to 2 from uncovered elements including itself and add it to elements 5, 10, 8 and 0 in A1, A4, C1 and C4 respectively, which lie in the intersection of two lines. Another revised table so obtained is shown in the table. Step 7. Repeat steps 3 to 6 to find a new solution. The new assignment is shown in this table since the assignments which is equal to 5 equals the number of rows or columns. The solution is optimal. The pattern of assignment among jobs and employees with their respective time is given in the table. Example 2. A computer center has 3 expert programmers. The center wants 3 application programs to be developed. The head of computer center, after carefully studying the programs to be developed, estimates the computer time in minutes. This is required by experts for application program as follows. Row represents 3 expert programmers 1, 2 and 3 and column represents the application program A, B and C to be developed. Values on the table represent the computer time in minutes required by the experts for the application programs. Assign the programmers to the programs in such a way that the total computer time is minimum. Solution. The Hungarian method is used to obtain the optimal solution. Step 1 and 2. The minimum time element in rows 1, 2 and 3 is 80, 80 and 110 respectively. Subtract these elements from the elements in their respective row. The reduced time matrix is shown in the table. In the reduced table, the minimum time element in columns A, B and C is 0, 10 and 0 respectively. Subtract these elements from all elements in their respective column in order to get the reduced time matrix as shown in the table. Step 3. Examine all rows starting from the first, one by one, until a row containing only single 0 element is located. Here rows 1 and 3 have only 1 0 in the cells 1C and 3A respectively. We assign these with zeros. All zeros in the assigned column are crossed off as shown in the table. We now examine each column starting from A in the table. There is 1 0 in column B in the cell 2B. Assign this cell as shown in the table. Since the number of assignments is equal to 3, which equals to the number of rows, the optimal solution is obtained. The pattern of assignments among the programmers and programs with their respective time is given in this table. Here's a summary of our learning in this session where we have understood mathematical model of assignment problem, the solution methods of assignment problems, the variations of assignment problems, the traveling salesman problem, and the typical assignment problems.